Welcome to the Deep Dive. We're your shortcut to getting truly informed on the big topics. And today, well, it's a huge one. Decarbonizing global industry.
It really is. Think about steel, cement, chemicals, these energy-guzzling sectors. They're fundamental, but they pump out about a fifth of all global greenhouse gas emissions.
That's massive. It's a really tough nut to crack for the climate challenge.
Absolutely. Now, for years, the scientists have pointed towards electrification, right? Either using electricity directly or indirectly, mainly by using it to make hydrogen.
Right, and hydrogen. Well, it's really captured the imagination, hasn't it? Especially among policymakers. You hear it talked about almost like a silver bullet for these sectors.
That's the perception, definitely. The hydrogen economy is a very compelling idea.
But is it really the silver bullet? Is it the only answer, or even always the best answer? That's what we're digging into today.
Exactly. We're going to challenge that perception a bit using a fantastic new research paper as our guide.
It's called Electrification versus Hydrogen, a data-driven comparison framework for energy-intensive industries. Quite a mouthful, but really important work.
It is, because it gives us this data-driven comparison pathway against pathway for specific industries. It moves beyond just generalizing.
So think of this deep dive as your fast track to understanding this really critical piece of the energy transition puzzle. We're going to pull out the surprising bits, the practical stuff from this study.
Yeah, hopefully you'll get some real aha moments, a more nuanced view than you might get from the headlines.
Okay, let's dive in. These energy-intensive industries, or EIIs, we mentioned steel, cement, chemicals, but also things like non-ferrous metals, glass, pulp, and paper. Huge emitters, like you said, around 20% globally.
And the tricky part isn't just the emissions volume. It's these incredibly long investment cycles, we're talking decades, for a plant, and the sheer amount of capital involved. They need to start changing now, but it costs a fortune.
So pathway one, direct electrification. What does that actually mean in practice?
Basically, it means swapping out fossil fuels, gas, coal, whatever, and using electricity directly in the industrial process. Ideally, that electricity comes from renewables, of course.
Makes sense. Maximize efficiency, cut out the middleman, so to speak.
Pretty much. Fewer energy conversion steps means less energy lost along the way. It's got huge potential, but it can be tricky for processes that need really, really high temperatures, which many of these industries do. Getting heat electrically isn't always straightforward at that scale.
Okay, and then the other main route, indirect electrification, which mostly means green hydrogen.
Right. So here you use renewable electricity, but you use it to make something else first, in this case, hydrogen, through electrolysis. That hydrogen then becomes your fuel or feedstock, or you might convert it further into things like ammonia or methanol.
And green hydrogen, made from renewables, is widely seen as essential, right?
Yeah.
Especially for things that just can't easily use direct electricity.
Absolutely. It's definitely going to be a key part of the future industrial landscape, no question. But, and this is where the study comes in, maybe it's not the only answer or the universal answer people sometimes assume it is.
So the common narrative is maybe a bit too simplistic.
That's what this study suggests. It really puts the spotlight back on direct electrification and says, hang on, let's look closely at the advantages here, which often get a bit overlooked in the hydrogen hype.
So how did this study actually compare them? What makes its approach different?
Well, a lot of previous work was, more qualitative, giving broad overviews, or zoomed in on just one sector, or it used models that optimize for maybe just cost or just CO2, which misses a lot of the real-world complexity.
Right, the practicalities.
Exactly. So this study tried to fix that. It combines quantitative data with qualitative insights, and it looks across multiple sectors for a direct comparison.
Which sectors did they focus on?
4 key ones. Cement and glass, those are non-metallic minerals, and ammonia and methanol, which are basic chemicals.
Okay, why those 4 specifically?
They're huge emitters themselves. Together, they account for about 9% of global CO2, and nearly 50% of all emissions just from these energy-intensive industries. So tackling them is a really big deal.
Got it. And the method they used, this multi-criteria decision analysis, MCDA, how does that work?
So instead of just looking at cost, or CO2, they use 11 different criteria. They grouped them into technical, economic, and ecological factors. Things like how mature is the technology? Can we use existing infrastructure? How efficient is the process? What are the safety implications? What about land use?
So a much broader view.
A much broader, more holistic view. They were careful to pick criteria that were, systemic, consistent, measurable, comparable, all the good stuff you need for a robust comparison.
And you mentioned they didn't use CO2 emissions as a criterion. That seems Counterintuitive.
It does at first glance, but their logic was really clever. They argued that both pathways, if you power them with 100% renewables, could potentially eliminate all the operational CO2 emissions.
Ah, okay. So if both can theoretically get to zero CO2, the real question becomes,
Exactly. What else matters? What are the other trade-offs? What differentiates them in practice beyond just the carbon footprint? That's the core question this study forces us to ask.
that it really shifts the focus. So what did matter most according to the experts they surveyed? They talked to 38 experts. Right?
Yeah, from research institutes, NGOs, think tanks. And the number one factor, the one ranked highest, projected energy costs.
No big surprise there, I suppose. Cost is always king.
Pretty much. But other things ranked highly too. Technological maturity. How ready is this stuff to deploy?
Yeah.
Process efficiency and safety. Those were all seen as really crucial.
And what was less important, surprisingly?
Using existing infrastructure and process flexibility, that was interesting. It suggests the experts were thinking long-term, maybe prioritizing the best future solution over the easiest immediate fit with what we have now.
Okay, so let's get to the results. This is where you said it gets really interesting. What did the data actually show about direct electrification's advantages?
Well, the overall finding was pretty clear. Direct electrification often comes out ahead on several key metrics that are frequently overlooked.
Like what, specifically?
Okay, take land use. Counterintuitively, the study found direct electrification generally requires less land area for the renewable energy generation needed per ton of product in 3 out of the 4 industries they looked at.
Less land. How does that work? I'd assume direct electricity needs massive solar farms or wind parks right nearby.
You avoid the extra energy needed for electrolysis and potentially hydrogen transport or storage, meaning the total renewable generation required can actually be lower, which translates to less land. It supports more decentralized energy too, potentially reducing land use conflicts.
That's a fascinating point. What else?
Air quality. Not NOx emissions, nitrogen oxides. Direct electrification basically eliminates them during production because there's no combustion happening.
No burning, no non-ox. Simple as that.
Pretty much. Which means less smog, less local air pollution. That's a huge co-benefit, especially for communities living near these industrial sites, particularly for cement and glass plants.
Okay, so less land, cleaner air.
Yeah.
What about costs and operations?
On costs, the study projects lower energy costs for direct electrification, especially looking ahead as renewable electricity prices continue to fall. Safety also scored better. Hydrogen is explosive, and industry just has a less large-scale experience handling it as a fuel compared to electricity.
And flexibility. You mentioned that was ranked lower by experts, but how did the pathways compare?
Right. Even though experts didn't prioritize it as highly, the study found direct electrification technologies were actually more flexible in responding to fluctuating renewable power in 3 out of 4 cases. That's a big plus for grid stability and potentially tapping into cheaper electricity tariffs when supply is high.
And capital costs, building these new plants.
For new builds, CapEx was found to be lower for direct electrification in glass and ammonia production specifically. And just raw process efficiency was better for direct electric glass melting and something called electrocatalytic ammonia production.
Wow, okay. That's a pretty compelling list of advantages for direct electrification.
It really is. It paints a different picture than the typical hydrogen-centric view. But of course, hydrogen definitely has its own strengths, and it's still absolutely vital.
Right. It's not being dismissed entirely. So where does hydrogen shine in this comparison?
Infrastructure is a big one. The study points out that our existing natural gas pipelines might be partially repurposed for hydrogen. That's a potential advantage.
So less need to build entirely new networks from scratch.
Potentially, yes. And for existing factories, retrofitting might be simpler, maybe just swapping out gas burners for hydrogen burners rather than redesigning the whole heating system for electricity. That perceived lower barrier can be really attractive for industry.
I can definitely see that. Less disruption, potentially lower upfront costs for an existing plant.
Exactly. And related to that, the study found that hydrogen technologies generally have higher technological maturity right now, especially in the supply chain. They're closer to being market-ready at scale.
Meaning they could start cutting emissions sooner, even if direct electric options might be better long-term.
That's the trade-off, yeah. And on the CapEx point, again, while new electric plants might be cheaper in some cases, this study showed that for refurbishing existing plants, hydrogen technology consistently came out cheaper across the board.
Okay, that's a really important distinction. New build versus refurbishment.
A very key distinction.
Hmm.
And then you have specific industries where hydrogen just performed better overall in this analysis, like cement, where it had slight edges in efficiency and capex, and particularly methanol production, where hydrogen was a clear winner, mainly due to its higher tech maturity and efficiency.
So it really depends on the specific industry and the situation. New plant, old plant, specific process needs.
Precisely. Let's maybe zoom in on those industry specifics a bit more based on the study.
Good idea. Let's start with cement. You said hydrogen had a slight edge.
Yeah, slight edge for hydrogen in the study, but overall scores for both pathways were relatively low compared to other sectors. Cement is just really hard. And it's crucial to remember most plans for decarbonizing cement rely heavily on biomass or waste fuels anyway, and pretty much all deep decarbonization options for cement still need carbon capture, CCU, or CCS on top.
Okay, so cement is its own complex beast. What about glass?
For glass, this study showed direct electricity scoring higher. That was mainly driven by better process efficiency, safety, and obviously the zero NOx emissions benefit we talked about. But interestingly, industry roadmaps for glass are exploring both routes and even hybrid systems.
Hybrid, using both.
Yeah, we'll come back to that. For ammonia, the scores were actually high for both pathways in this study. Direct electricity just squeaked ahead slightly, mainly due to lower capex for new plants and better process efficiency, particularly for electric catalytic methods.
And ammonia synthesis via electrocatalysis is considered more mature than for methanol, right?
According to this study, yes. Which brings us to methanol. Here, hydrogen was the clear winner. Why? Mainly because the direct electrocatalytic route for methanol is just, well, it's way behind. Very low technology readiness level, or TRL below 4. It faces huge hurdles.
TRL below 4.
Yeah.
That's basically still lab-scale research, isn't it?
Pretty much. Years, maybe decades, away from commercial reality without major breakthroughs. So for methanol, established hydrogen-based routes look much more viable in the near to medium term based on this analysis.
So it really underlines that it's not just electrification or hydrogen. It's much more granular.
Exactly. And that brings us to the idea of hybrid solutions you mentioned. This study touches on it too, the possibility of combining direct electricity and hydrogen to kind of get the best of both worlds.
How would that work?
You could imagine, so running primarily on direct electricity when renewable power is abundant and cheap, but then switching over to stored hydrogen when the sun isn't shining or the wind isn't blowing. It gives you flexibility, resilience.
Hedging your bets, in a way.
Sort of. It avoids putting all your eggs in one basket, especially while some of these technologies are still maturing. Which brings up another point the study flags, the valley of death.
Ah, yes, the dreaded valley where promising tech goes to die.
Exactly. Those electrocatalytic routes for ammonia, and especially methanol, they're promising, but they're stuck at low TRLs. Getting them from the lab, TRL4, through demonstration, TRL6, requires massive investment and risk-taking. Without strong support, they could easily falter in that valley.
And we should also remember, as this study implicitly acknowledges, that even if direct electrification wins for heat, hydrogen is still essential as a feedstock in some industries, right?
Absolutely critical. Think about steel production using direct reduced iron, or DRI. That needs hydrogen as a reducing agent. Direct electrolysis of iron ore is another electric route, but its TRL is currently very low. So hydrogen's role as a chemical reactant is separate from its role as just a fuel.
Okay, stepping back to the big picture system-wide implications, what are the major roadblocks this study identifies?
The big one is infrastructure. For either pathway to work at scale, we need huge upgrades. The electricity grid needs massive expansion and strengthening. We need hydrogen pipelines like the proposed European hydrogen backbone and storage. And energy storage in general, batteries or other forms, is crucial to handle the intermittency of renewables.
So it's not just about the tech in the factory, it's about the entire energy system supporting it.
Precisely. And that leads to the economic and policy needs. This study is clear. Right now, these innovative electric or hydrogen processes are generally more expensive than using fossil fuels, even with projected cost drops for renewables.
So we need governments to step in.
Definitely. This study talks about needing both push and pull measures. The push comes from things like higher carbon prices, making pollution expensive.
Making the old way less attractive.
Right. And the pull comes from policies that actively support the new technologies. Things like creating markets for green steel or green cement, green lead markets, or using financial instruments like carbon contracts for differences to guarantee a price for low carbon production, making investment less risky.
And they mentioned things like the Carbon Border Adjustment Mechanism, CBAM, in Europe.
Yeah, that's crucial to prevent carbon leakage, basically stopping companies from just moving their polluting factories outside the region to avoid the carbon costs. It tries to level the playing field.
There was another interesting system effect mentioned, the renewables pull effect.
Ah, yes. This is the idea that access to cheap, abundant, renewable energy could become a primary driver for where industries locate in the future.
So factories might actually move to sunny or windy places.
It's a real possibility discussed in the context of this study's findings. We could see a geographic shift, with industrial heartlands potentially relocating to areas rich in low-cost renewable electricity. Think deserts for solar, coastal areas for wind.
Wow, that has huge implications for jobs, trade.
Massive implications. This study hints at how developing countries with great renewable resources might gain an advantage, especially if mechanisms like CBAM ensure their low-emission products aren't undercut. Meanwhile, traditional industrial regions might face pressure. It's a potential reshaping of the global economic map.
Of course, like any study, this one has its limits. We should probably touch on those.
For sure. The authors are upfront about it. Choosing and weighting those 11 criteria, there's inevitably some subjectivity there, even with expert input. They also had to limit the scope, so social impacts, geopolitical factors, those weren't explicitly included.
And the future is always uncertain, especially for technologies that are still pretty early stage.
Exactly. The study assesses long-term potential, but it acknowledges that the less mature technologies, particularly the electrocatalytic ones, aren't going to be major players overnight. They need that R&D push we talked about.
So let's try and wrap this up. What are the absolute key takeaways from our deep dive into electrification versus hydrogen, a data-driven comparison framework for energy-intensive industries?
I think number one is that energy cost is absolutely king. That came through loud and clear from the expert survey. Number two, direct electrification offers some really significant, often underappreciated advantages: lower projected energy costs, no NOx pollution, potentially less land use. It really challenges the hydrogen is the only answer narrative.
But crucially, hydrogen is still vital, right?
Absolutely. It wins out where its technological maturity is higher, where existing infrastructure gives it an edge, especially for refurbishments, and in specific sectors like methanol or as an essential feedstock like in steel.
So the real message is nuance. It's not strictly either.
Not at all. This study strongly suggests it's often going to be both hand. We'll likely see hybrid solutions, and the best path will vary hugely depending on the specific industry, the location, the availability of renewables, the state of the infrastructure. It's context dependent.
And the bottom line for getting this transition moving.
Action needed now. The study is a clear call for policymakers to provide support, financial incentives, clear regulations for both energy carriers, and for industry to step up investment in pilot and demonstration projects to scale these technologies. We can't afford to wait if we want to hit climate targets.
Okay, a final provocative thought to leave our listeners mulling over.
Well, building on that study, think about those electrocatalytic processes, especially for chemicals like ammonia and methanol. If, and it's still an if, they overcome that valley of death, could they enable a totally different way of making chemicals? More decentralized, smaller scale, more flexible plants located right next to renewable energy sources, challenging the huge centralized chemical complexes we have today. It's a potential future that this electrification versus hydrogen, a data-driven comparison framework for energy-intensive industries, helps bring into focus, and definitely something to watch.